All right, so in this video, we're going to record our last section of probability notes for Unit 2, Unit 3, and we're covering conditional probability and Bayes' rule, an application of conditional probability. So I'm going to review. Previously, we talked about something called independent events. So independent events are ones where the probability of one occurring does not affect the other. So probability of A and B occurring is probability of A times probability of B, right? Some more review if you want it. Mutually exclusive events means they both can't happen at the same time. Probability of A or B occurring is probability of A plus probability of B. Because of course, probability of A and B occurring is 0. Okay, so that's some review. In this video, we're talking about conditional probabilities, events where they are not independent. They may impact each other. And so we have to have caution. These rules here don't apply anymore. We have to have caution. Many events actually are related. So an example from this class, example I could think of is like if you have power, like maybe there's a storm and it affects whether there's power or not. If you have power, that might affect whether there's a likelihood of being in class on a given day. Or if there's not power, there's maybe a higher likelihood of not having class, right? So these two events are likely to be dependent, okay? So let's just do a couple warm-up problems with this. Probability, I'm going to call having class being A, no class is not A. Having power is B, having no power is not B, okay? Just to make it easy. And so, oh, whoops, I haven't switched here. I'm going to be consistent with what I say here. Power is A, no power is not A, B and no B. Okay, sorry about that. So what's the probability of having class on any given day? Okay, that we could just look at, well, there's, of all the classes, 90 times we met out of a total of 100. So 90 out of 100. So let's do something else. What's the probability of having no class? Well, probability of not be is going to be 10 out of 100. 10 classes out of 100, so 0.1. And these are what? Complementary events. Okay, so some more of the terminology we've been using. So next thing I want to know is, what if I wake up in the morning and there is power? What is the probability that I have class? This can be written as probability of having class given that there was power. Okay, this is read probability of B given A. And in that case, we look at this situation where we know A has occurred. Suppose there is power. Probability of B given A is going to be 90 times we had class when there was power, out of a total of 96 times there was power. Okay. Or we could say the probability of no class given power. And that would be, okay, there was 6 times we had no class out of the total times there was no power. Okay. So 90 out of 96 is 93.75%. 9 out of 96 is 9.375%. Oh my goodness, these percentages are different. It seems like, oh, okay, so these are different, maybe no surprise. Now let's look at something else. What's the probability of having class given no power? Given no power, we're looking at this situation here. Given no power, there's 0 events. out of a total of 4. So that's a 0% chance. And the probability of no class given no power, go away. Excuse me. Would be nope, no class given no power is going to be 4 out of 4, 100%. So what I want to say is the probability of B occurring really depends on whether or not A has occurred, right? These probabilities are dramatically different. And same for these two. So when we are calculating events that are conditional, the probability of A and B occurring can be found from probability of A given B times probability of B. So let's check that. What's the probability of A and B occurring here? Well, A and B occur 90 times out of 100. What's the probability of A given B? We found that. Let's find that. A given B. What's the probability of A given B? So given that B has occurred, A occurs 90 out of 90 times. And probability of B occurring was 90 out of 100. So this formula checks out in all these different cases. You could rearrange A and B, and that's how conditional formulas work. So what I want to use this for then is these rules, this mathematical formula that I've introduced, can be used and manipulated, and we do some stuff to get an equation. So the formal math is here. I don't want to talk too much about it. You can read it if you're interested in how I'm combining these rules. But you do some work to find out a way to rearrange probabilities, to invert probabilities. If I know B given A, I can invert them using this formula called Bayes' rule. So this is a formula that we're going to use in this class. If you're curious where it comes from, go ahead and read the notes. But I want to use it. So for an example of testing a disease, suppose there's like a new COVID test, and we want to know like how accurate is it? How good is it for using? And so we have this information about a test. And so the information is it's got an incident rate of 10%. It affects, 0.1%. It affects that much of the population. It produced no false negatives. That's good. But there's a false positive rate. So this is information that we can use to find out from this problem. What we really want to know is probability of having the disease given that you test positive, right? If you test positive, there should be a high chance that you have the disease. And so we'll see with this problem how this works. I'm going to show it two ways. Method 1, I'm going to use a table. Method 2, I'm going to use this actual formula up here. So I'm going to let you choose which method you think makes the most sense. So method 1, the table involves just listing all the possible outcomes. So you either have the disease or you don't, or you test positive, or you test negative. So these are the different cases. And just think for a second, which are the cases that are accurate? You're correct. The disease is correct when you test positive and have the disease, or when you test negative and you don't have the disease, right? Happy in the sense that the test was accurate, not that it's good to get a disease, but the cases where it's incorrect are here. So the way we're going to plot out this problem is use this information here to fill in the table. And we start by looking at what the totals are, the row and column totals. And so we can pick any number to put here. 10,000 is a good number. And this is just giving us relative proportions of the different parts of this table. So let's start with this first piece of information. The disease affects 0.1% of the population. Okay. That means 0.001, that's 0.1% divided by 100 is how we get this to a decimal, times 10,000 gives us the total people that have the disease. So that ends up being 10. And the remaining 0.999% times 10,000 gives us the people that don't have the disease. So 9,990. And right, these add up to, they add up to 10,000. Right. Okay, let's look at our next piece of information now. Test has no false negatives. Where in this table is a false negative? Well, here you have negative and it's false. So that would be the false negative rate. And false negatives, there's none of them. So this cell is 0. There's 0 people that get false negatives, meaning out of the 10 people that get the disease, they all test positive. So these columns add up. These, the column adds up to 10. All right, so we got that piece of information. And lastly, the false positive rate is 5%. Where in this table is false positive? Here is the false positive. And so if 5% of the people that get disease test positive, that means 0.05 times 9,990 gives us the false positive rate, which is 499.5. That's nice. We can use that information then to calculate the total number of people who test positive. And then you could find out the remaining amount. This cell plus this cell has to add up to 9,990. So we get 9490.5. And then we can get the column sum to be 9490. Did I do that right? Yeah, because there's no people here. Okay, so once we fill in this table, we can find any conditional probability we want. So finding the probability of having the disease given positive is you look at, okay, I tested positive, given positive, that's going to be this column here. So probability of having the disease given positive will be 10 over 509.5. So that ends up being 0.0196, so 1.96%, about 2% is the probability of having the disease given that you test positive. So that's actually not a very good test. Like even doctors take this information from this test and think, hey, this is a good test. But it tells you that if you test positive, there's still only a 2% chance that you have the disease. So whether you realize it or not, in solving this problem, we did use Bayes' method. We made all these calculations in an intuitive way. So if you like the table, go ahead and use that. And that's it. If there's another method you want to see, if you like using formulas or programming, I'm going to use the formula now to solve this in what I will call method 2. This is the formula method. And it's good to have multiple approaches. So if you understand both methods, you're ready to go. Okay, so with this method, I'm just going to fill in what all these values of my Bayes rule, here's Bayes rule. I'm going to find out what all these individual parts are. So I can find out the probability of disease given positive. So probability of the disease is the incident rate, actually, 0.001. That's how many people proportionally have the disease. So not having the disease is going to be the complement of that, right? You either have the disease or don't. So that's going to be 0.999. So we got that first piece of information. Next, let's look at the false negative rate. 0 people have the disease given that they test positive. Wait. Say it again. yeah, given that you have the disease, you will test positive, meaning no one tests negative. So this is the false negative here. And that's going to be 0. No one tests negative when you have disease. Meaning these are complementary, meaning if you have the disease, you're going to test positive, 100% likelihood. So those are complementary. And lastly, let's look at this third piece of information. The false positive rate is 5%. The false positive rate is when you test positive and you have the disease. So that would be 5%. And testing negative and not having the disease is also complement to that. So if you have the disease, if you don't have the disease, and you test negative, that's going to be the 1 minus 0.05. Okay, so once you have all these pieces of information, you can simply plug them into this formula and calculate it. And here's some math for that. And you get the same result. So there you go, 2 methods for doing what is really a pretty confusing problem to most people. But if you break it down, you have a pretty valuable mental tool for inverting conditional probabilities. All right, so I'll stop here. We'll do another example in class. Take it easy.